To model and solve a basic problem using the capabilities of the Express Python interface, in a new Python file, start by importing the Express package. Since all types and methods must be called by prepending the word express, it is advisable to alias the module name upon import and prepend the alias instead. You can obtain a complete list of methods and constants available in the module by running the Python command dir express in a command line, or by printing it within your Python script. Then, use the xp.problem class to create a new problem instance. Optionally assign a name to the problem by specifying the name argument. To create and directly add new variables to the problem, use the problem.addVariable function, which takes 5 optional arguments, whose description you can read on this slide. These include the variable name, lower and upper bounds, and a threshold which is needed for some of the 6 variable types available with Express. Variables added to an Express problem are constrained to be non-negative by default. To create an unbounded variable, its lower bound must be specified as -xp.infinity. A set of variables can also be created via the same method using Python's fundamental data structure, lists and dictionaries. In the case of a list, a zero-index set of variables is created and added to the problem. If more elaborate indexing is required, dictionaries can be used, which allows the user to refer to such variables using the values in the list, such as in the example shown. Variable names can be useful to identify variables in saved files or print statements for debugging purposes, and to query the problem for those variables. If the variable name is not explicitly specified via the name argument, the variable will be assigned an automatically generated name consisting of a C, followed by a sequence number. In any case, when querying for a variable or expression containing that variable, the variable name will be returned rather than the Python object used in the program. For creating an indexed set of variables, you can use the function problem.addVariables. It takes one or more additional arguments denominated as asterisk indices, each being a list, a set, or a positive integer. If the indices argument contains only one list or set, a variable will be created for each element in the list. In case more than one list or set objects are passed, variables will be created for all pairwise combinations between the elements of the lists or sets. Create constraints in a natural way by overloading the less than or equal, and greater than or equal operators in their definition, such as in the examples shown. It is possible to add a new constraint by passing the full form expression directly as an argument to p.addConstraint, either as a single constraint or a list of constraints. To add several constraints to the problem with one call, simply pass those constraint objects as arguments in p.addConstraint. Each argument can also be a list, tuple, or array of constraints. Constraints can be created from lists and dictionaries, just like in the example shown. A list of strings is created and used to generate a list of expressions, and a dictionary where constraints are created for all pairs of names. For your convenience, the Express native sum operator can help formulate problems by summing the elements of a list in a compact way within an expression, such as in the examples. In case you want to provide a name for your constraints, use the xp.constraint class instead. It is possible to create a constraint by stating the complete constraint as argument, or by specifying the different elements in individual arguments such as body, bounds, type, and name. In the first of these examples, a constraint is created by passing the complete constraint expression, while in the second example the same constraint is created by passing the individual arguments. Besides being able to define a name, the Express.constraint class can be particularly useful for creating range type constraints, in which case a lower bound and an upper bound arguments are required for the constraint. To create and add an objective function to the optimization problem, you can use the setObjective method of the Express package. An objective argument must be passed containing the expression that defines your objective, with the optional parameter sense defining the sense or your optimization. By default, the objective function is to be minimized, so in case you want to set an objective to be maximized, explicitly define the sense attribute as xp.maximize, as represented in this example. The Jupyter Notebook example modeling.ipynb, available in the public Git repository named FICO Xpress, demonstrates the use of the basic modeling API methods. After importing the Express package, two objects are initialized, an integer and a set, and a new problem is created. A name can be assigned to the problem upon creation by using the name argument. Then, variables are created and added to the problem using the add variable method. First, a variable v is created for each element of set S with only one line of code, where variable names are defined according to the variable index. Variables v1, v2, and vb are created separately where some arguments such as name, bounds, threshold, and variable type are explicitly specified. Several constraints are then added by using the add constraint method, which receives a list of arguments that range from an explicitly created constraint object to two constraints defined inline via expressions, and lastly a set of constraints indexed by members of set S. Then, the objective function is specified via the setObjective method, with the sum operator being used to model the scalar product between the v variables and the elements of set S, which serve as coefficients. The sense argument further indicates that the optimization problem is to be minimized, although that would be the default value of this field in case it was not defined. By running all code cells of the notebook, the results for the optimization problem that we have defined can be observed in the solver logs in the output cell at the bottom of the notebook.